Welcome to my brief introduction of Huygens Principle. Huygens Principle states that every point on a wavefront is a source of wavelets that spread out in the forward direction at the same speed as the wave itself. Huygens Principle can be used to explain how waves behave. This includes water waves, sound waves, and light waves. First, I will show you what Huygens Principle means by drawing a side and a top view of the wave. So first, the side view of the wave has the peaks and the troughs. Next, the top view has just the peaks shown as the wave moves towards the right. On top of these peaks, there's wavelets, as Huygens Principle states, and these wavelets are spreading outwards, as I will show with circular movement. These wavelets are at all points of the wave, and they mimic the wave that is shown afterwards. The new wave front is tangent to the wavelet so that this new wave becomes the next wave with the same frequency. Huygens Principle can be used to explain different properties of waves, which is included propagation, the laws of reflection and refraction, and also can tell us how light rays interfere with each other either constructively or destructively. Huygens Principle allows us to understand how waves propagate. An example of this is a flashlight. The waves from a flashlight doesn't travel straight outwards. Instead, it's more like a pebble dropping in water, how the waves expand outwards to fill a larger space. So as the light travels through the torch and leaves, it expands outwards as it propagates. Another way of viewing this is the top view of a light or sound or water wave travels through, and it has equal amounts of lines, and then as it travels to a gap in the hole, it expands outwards through that hole because of the wavelet that reaches the hole. And then another example I will show you is when a wave is traveling around a corner into another room. Like how you can hear like your mother in the hallway when you're in your bedroom, light can travel through the slit, and then as it goes around the corner, it continues onward. And then there's another hole in your bedroom that the light then goes through outwards again. Like the pebble dropping in the water, it propagates outwards. The next principle Huygens helps us explain is the law of reflection. So as light travels towards a mirror, it reflects off the mirror at the same angle that it made impact. And the waves are the same size as when they made impact and after impact to the mirror. Huygens' law of refraction is explained a little bit differently because a wave is traveling through two mediums. For example, we can say that the medium 1 is air and medium 2 is water. So as the wave travels through the medium 1 at an angle, when it hits through medium 2, it changes angle so that the waves, when it travels through, is different. Instead of a straight wavefront traveling through, it bends since the wavelets have a lower speed in the second medium. This could be an example of light traveling through water, and then when you look straight downwards, the object that you see in water isn't exactly what it appears to be. In 1801, there was a man named Thomas Young. He helped convince Einstein, who didn't believe that Huygens' principle could apply to light waves. Thomas Young was able to show through his double slit experiment that light actually did behave the way that Huygens predicted. What he did was he had a light shine through two slits, and on the opposite side of the slits there was a wall. Instead of seeing just two slits of light on the opposing wall, Thomas Young noticed that there was multiple slits of light with varying widths on the opposing wall. We can show an example of this by drawing a top view of the light going through two slits. If we do it according to Huygens' principle, those light slits have propagations of the wavelets going outwards. Within those propagations, there's an interference between the two different lights. I will draw the marks where there is constructive interference. This is when the peaks of the opposing waves actually meet together. There's destructive interference when a peak matches a valley of another wave. In another view of this, I'll draw a horizontal view of these waves. So constructive interference and destructive interference interact differently. Showing a side view of these waves, we can see how these waves interact with each other. In constructive interference, where I showed you where there's peaks matching together and the valleys in destructive interference, the peaks and the valleys are going opposite of each other. So as a result, in constructive interference, you have a resulting wave that is larger than the two waves on their own. In destructive interference, these two waves interact with each other and cancel each other out with no wave. Going back to the top view of a light, we can see that where there is constructive interference, there would be a light shown on the opposing wall. Where there's destructive interference, you would see no light being shown. Thus, the result of Thomas Young's experiment shows that light does act as Huygens Principle predicts, as light is shown and then spaces between that light is where destructive interference is happening. Thank you for watching my lesson on Huygens Principle.